Assalamu alaikum, dear students. I'm going over quick Unit 3 and 4 revision. And remember that this is just 2 or 3 hours revision, and it's not going to cover every single topic in your chemistry. So when you prepare for exam, and right now you're doing that, you need to make sure that you cover all the topics, all the dot points from study design. But what I'm going through is that I found some deficiency in you guys and some topics which were difficult for you. Just touching on those topics, and I'm going over those. So this recording will be available to you, and I'll also print out these notes, I think 34 pages or so, for your reference, and I'll give it to you, the hard copies as well, on Monday. Now, I'm going in order of your textbook. I'll record with significant figure, then energy, then the redox reaction, galvanic cell, and then rate of reaction, and so on. I'll follow the order which is in your book and only touch the important topics, not every single topic. I want you to listen to this recording now, and also on your last day, like if you have an exam tomorrow, so the last night, I want you to listen to this recording again. It's very important. All right. I'll start with the important suggestions. So you have 2 hours and 30 minutes for writing, 15 minutes for reading. First suggestion I want to give you is do not waste 15 minutes reading time. Now, what does that mean? I see during the SAC or trial exam, I noticed that students just sitting around and waiting for this 15 minutes to finish, and then so they could start writing the actual exam. Remember that these 15 minutes are part of your exam, and you have to do something during this 15. You can't write, so what you can do? So use this time to plan the answers, especially, in your exam, there are sometimes very difficult, complicated diagrams. Sometimes you see very difficult, hard to understand diagrams from galvanic cell, electrolytic cell. So you just use that time, this 15 minutes, try to understand those complex diagrams. And every year we have one question which is experimental, like they give you all the data and you have to read like half page or maybe 1 page, read the tables. Go to that experimental detail during this time, read the experiment, try to find out and analyze the data during this time. So this is very important time, 15 minutes. I recommend that. Just don't read every single question. Just go to the hard questions, for example, where there are big complicated diagrams, or go to experimental question, read experiment, try to understand what the experimenter is doing, try to analyze the data. 15 minutes up already. All right. So when you start writing, you may start with MCQs. Many students want to do that. But remember that you don't want to spend forever on MCQs. You have 90 marks coming from your short answers and the section B, and maybe 30 marks only coming from MCQs. So you don't want to spend more than 30 or 40 minutes on MCQs. Just as soon as you already cross 30 minutes, 40 minutes, start section B. Even if you have done 20 out of 30 MCQs, it's okay. You can come back always. But section B must be started within 40 minutes of your writing time. All right, very important. And when you write the answers, you see there are borders on your answer page. Do not write outside the border, because the assessors receive the scanned copies of the answers. So if anything is outside the margin, they may or may not see your words or the answers outside the table. So make sure you write within the borders, and you try to use black pen or blue pens, because they're more visible. Make assessors' life easier. They want to read your answer and give you marks, but if they can't read because the handwriting is too bad or it's written too light, they can't see your answer, it's hard to give for them to give you marks. So make sure you use black pen or blue pen for your answers, good handwriting and clearly stated answers. And then in numerical questions, show all the working out steps. So if there are 4 marks question, it's a numerical question, and you just do all the calculations in your calculator and write the answer, trust me, you'll not get more than 1 mark or maybe 2 max. So you need to show the working out step. If this is a 3 mark or 4 mark question, there are marks for step 1, finding moles. There are marks for step 2, maybe finding the mass. So show all the steps that you have done so you get full marks. If there is just 1 mark question, try to show at least formula or something. But in 1 mark question, you may get 1 mark if you have done everything and then answer is correct with the units. But still, even if 1 mark question, try to show something like how did you find the answer, maybe formula, yeah. But in 3 to 4 mark question, definitely you want to show 2 or 3 steps, whatever steps are involved in that question. All right. Now try to box your answer. Like if you have answer, for example, 2.3 kilojoule per mole, something like that. First of all, your answer should have units. Without units, you may not get full marks. All right. And once your answer is there, try to box it, because this will make sure that assessor right away sees the answer. Oh, answer is there, and then he can maybe she can backtrack the working out as well. Now, one common thing among the students is that if there's a very difficult question, they could not do it. It sucks their energy. This 2 hours and 30 minutes is very important for you guys. You don't want to lose your focus during this time. You don't want to feel low during this time. So make sure that if there's a difficult question, it doesn't suck your energy. Just can't do it, it's okay. Just go to the next question. All right. So if you can't do a difficult question, do not lose focus or low energy. Do the next question with the same energy, with the same focus when you started the exam. All right. So you need to be at higher vibration all during 2.5 hours. You don't want to feel low. You don't want to have low vibes or low energy during this time. All right. Make sure the difficult questions don't control your emotions or your energy. Stay positive all the time, and you know that inshallah you'll do the best. This is before the revision, some suggestions. Now, significant figure, you'll have only 1 questions which you don't know. Assessors will be told to mark that questions for significant figures, which means that you can lose maximum 1 mark if you don't use significant figures correctly. But because you don't know which question is being marked for a Sig Fig, you have to treat every single question as that question, and you need to be careful with your Sig Fig marks, Sig Fig calculations. Now, this is from your VCEE website. It says that if you're adding 2 numbers, this is your final operation. You're adding 2 numbers. So the first number has 2 numbers after the decimal point, and the second number has 3 numbers after the decimal point. Your answer must follow the one with smaller number of decimal points. Yeah, so your answer should be only 2 numbers after the decimal point. This is when you're doing plus or minus only. If you're multiplying or dividing, you need to count the total number of Sig Fig. For example, if you're multiplying this number by this number and then dividing by this, all 3 numbers are there, but this number has 3 Sig Fig, the smallest number of Sig Fig. Your answer will follow this and will have 3 Sig Fig. So this is a simple rule, but you need to follow all the rules, which zeros are Sig Fig, which are not. Please go to your page, I think your textbook, page 562 or something. The details are there. Yeah, I'll just give you some examples here. It is from VCEE past exams. For example, they're trying to find energy raise. Don't worry about the question, just look at the final operation. They have 57 times this number and then adding this number. And so what's happening here, because the final operation, you multiply that, the final operation is addition, and you see that there are 2 Sig Figs here. Yeah? So your answer has 2 Sig Fig. If the answer looks like this, 3 4 0 0 0, you need to change this to the scientific notation to make this correct for Sig Fig. Now look at this one. There is addition happening here. Like I said before, that in addition you want to see how many numbers are there after the decimal point, because there's only one number after the decimal point. Your answer should follow the same thing. And yes, some question when finding the percentage, they don't care about the Sig Fig. You still need to have Sig Fig rules for percentages even. All right. Same as in this example. So you can, while doing some practice exam, make sure you also look at the solutions given to you. All right. So the Sig Fig, please make sure you understand that. Now, for in your textbook, chapter 1 and 2 is about energy, and most of the questions from these two chapters are asked about the definitions and also differentiate between this and this, advantages of this and that, comparison of this and that. So basically it's more of learning, not it's most of learning, not as conceptual questions, so many conceptual questions. So make sure you go to these chapters in your textbook, and towards the end read the summary points, and you have tables there. What is the difference between biofuel and this and that? Read all, basically memorize those. So I'll quickly go over some concepts there. For example, almost every year we have some question related to biodiesel and petrodiesel comparison. So remember that petrodiesel is a fossil fuel and biodiesel is a biofuel. All right. Petrodiesel is hydrocarbon. Only carbon and hydrogen is present. Yeah, only carbon. You see here, only carbon and hydrogens are present. While in biodiesel, there is long hydrocarbon chain, but at the end you have the ester group. All right, this is ester group. So now how it makes biodiesel different from petrodiesel? The first thing is that the petrodiesel has only dispersion forces because it is non-polar. It has only dispersion forces. All right, but this is polar. It has dispersion forces here on this part, but in addition to dispersion forces, it has those dipole-dipole bonds as well. All right. So because of this additional stronger intermolecular forces, the biodiesel is more viscous. Viscosity mean the stronger intermolecular forces. It is higher boiling point, higher melting point, all those things become higher. And while here you have only dispersion forces, so it is low melting, low boiling, and low viscosity. So once you know the structural difference, it makes sense that why so many properties are different. So petrodiesel is only hydrocarbons, no function group other than just carbon, hydrogen. Biodiesel is a long hydrocarbon chain plus ester group. Yeah. Now, how do you make biodiesel in the lab? So you take some triglycerides and mix it with methanol in the presence of catalyst and sodium, like sodium hydroxide. You'll form biodiesel plus glycerol or some alcohol, which you can remove. Now, you can find these comparisons in your book as well. What is the difference between petrodiesel and biodiesel? I want you to read these from these notes as well, from your book, and these as well, and kind of memorize this. Yeah. Now, another comparison is between two types of gases. The coal seam gas and biogas. Biogas, sometimes in the VCEE, they also use this term, landfill gases. Yeah. So remember that they are same thing. So biogas or landfill gases or coal seam gases was the difference. So coal seam gas is almost methane gas because 95% or more is methane gas. So basically whatever are the properties of methane gas are the properties of coal gas, so coal seam gas. So this is a fossil fuel, this is biofuel, it is non-renewable, it is renewable, and coal seam gas is obtained by mining and all those stuff. So read these as well. Yeah. What are the advantages and disadvantages? Now, same thing. You have biogas, no comparison, but how it is advantages and what are the advantages and disadvantages? Again, I'm not going to read everything. You just read and know that, memorize that, please. A very common question which is asked in the multiple choice question or short answer sometime, how if you have coals here, it has some stored energy in it. Yeah, everything has stored energy, but the things from which we can remove energy easily and can use it is called fuel. So coal here has stored chemical energy in it. We call that chemical energy. So chemical energy is stored in the coal. When you burn that, that energy is converted to thermal energy. Thermal energy then moves the turbine. Because it moves it, it becomes mechanical energy, and from the movement of turbine, the generator is turned on and it gives you electricity. So you need to know this flow of energy. So from the coal stored energy, it becomes thermal energy, then it becomes mechanical energy, become electrical energy. At every conversion point, some energy is lost, and because of that this is not very efficient, but the energy is lost at each point. So make sure you know that. And next is gases. The gases in your book, chapter 3. So for gases, you need to know some conversion, and some conversion are given in your data book. For example, a very simple conversion factor is that 1 ml and 1 cm is the same thing. All right. So if you're given that there's a container, it has 200 cm cube, or sorry, I said that 1 ml is equal to 1 cm. It's not 1 cm, 1 cm cube. So 1 cm times 1 cm times 1 cm. So if they give you 200 cm cube or they give you 200 ml, it's same thing. It is exactly same thing. Remember that. All right. So we can say that 1000 ml is equals to 1000 cm cube, or both are equal to 1 liter. So this conversion you need to know. In your data book, you are given, I think this is from your data book. You're given the relation between how many 100 kilopascal, which is equal to almost 1 atm atmospheric pressure, but 0.987. Exactly this number you will use if you have to convert, or 750 millimeter mercury. And 1 liter, this conversion is also given to you. 1 dm cube, they hardly give you what dm cube, decimeter cube, but they give you mostly liter conversion with cm cube and ml cube. So first thing you need to know for gas chapter, you need to know all this conversion, and you please use your data book. Your data book has this conversion. Try to make sense from data book, yeah, and this is from your book as well. So honestly, you should basically already know this without even data book. You need to know this conversion, most common conversion for ml and for kilopascal, the middle, this one, you need to know this. Save some time, yeah. Now about calculation, although most commonly we're expecting that you will use only this formula for your gas calculation, but I've seen in the past where you might have to use this formula: P1 V1 over T1 is equals to P2 V2 T2. All right. Now, if you know these two formulas, and of course the other common formulas like N is equals to M over capital M, if mass is given, you find moles like this. All right. And in addition to that, you can also use that relationship that 1 mole of a gas, 1 mole of a gas at SLC is 24.8 liter. This is the volume, molar volume. So molar volume is equal to volume is equals to N times Vm, and you can find moles from here. N is equals to V over Vm. All right. So this is Vm, or molar volume. So you need to know all these relations. So if you know these two formulas, you know this formula, and this conversion, you can do all the calculations. Now, what is happening here? In this formula, most important thing is that the R is given to you in your data book. So 8.31 is given to you in data book, but still make sure you use exactly the same number. So R is a constant, gas constant. It is given to you in data book. N is the number of moles. If number of moles are given, good. If not given, they might give you mass. So use this one to find moles. And T is always in Kelvin. Kelvin is whatever degree Celsius given to you plus 273, it will change it to K. Use K in this formula. Pressure is in kilopascal and volume is in liter. All right, you need to make sure that you know this, all this stuff. All right. So SLC is standard lab condition, is 298 Kelvin temperature and 100 kilopascal. All right. And Vm, which is molar mass of volume or volume of 1 mole of a gas at SLC, is 24.8 liter per mole. Now let's say this example. There are typical examples like this. Calculate the mass of a sample of neon gas which had a volume of this at SLC. Now first you need to find moles. Once you have moles, you can change it to mass as well. So we know that V is equal to N times Vm. All right. So to find moles, volume, which whatever volume given to you over Vm, which is 24.8, you'll find moles. So once you have the moles, multiply it by the molar mass of the neon gas and you'll find the mass. So make sure when you have the final mass, you box it and make sure you have the correct unit as well. Now there are different gas laws. You don't need to know all the gas laws, just these final two equations maybe will help you. Now this I told you already, that pressure should be kilopascal, volume should be liter, R is given to you in the data book, T must be Kelvin. In this equation, this side and this side, one mean before the change and two mean after the change. For example, they might say that, oh, there is a gas, its volume is this and pressure is this and temperature is this. They give you some initial condition. All they are ones, P1, V1, T1. And then they say that volume of the gas was doubled. Now they change this. Because of this one change, everything will change. So the new pressure is P2, the new volume is V2, not T2. So out of this sixth thing, they'll give you any two things and they'll ask you to find the one which is not given to you. All right. All right, after gas chapter 3 we have two chapters, chapter 4 and 5, which is redox and galvanic cell. So galvanic cell is chapter 5 in your textbook, but I'm not going over all the details of redox because I think that something you have done in chapter 11 and 12 again. So basically you need to know that what is oxidation, what is reduction, what is half cell, oxidation, reduction, and then redox. All right. So oxidation is loss of electron, reduction is gain of electron, redox is when the two half equations are there and you combine them, it becomes redox. And then you need to be able to balance that using this cohes maybe. All right, so first you balance the key element, then balance oxygen, then balance hydrogen, then balance the charge using electron, and lastly balance the state of your half equation. and once the half equations are balanced, you can add them to make full equations. So I'm not going into chapter 4's detail, but let's see chapter galvanic cell. And remember this oil rig, yeah? Oxidation is loss and reduction is gain. For galvanic cell, another statement I gave you in the class is like people love cats, yeah? So red cat is positive, and ox, who loves an ox? And ox is negative. All right. So this is true. This full statement is true for galvanic cell and for fuel cell. And this half statement, red cat and ox, is true for all the cells. All right. So red cat is positive and ox is negative is true for galvanic cell and fuel cell. But in case of electrolytic cell, it just reverses the last part. So red cat becomes negative and anox becomes positive for electrolytic cell. All right, because we're doing galvanic cell, so we keep this. So anox is negative, which means that oxidation always occurs at anode, and anode is negative. So if you know these things, you're already solving 3 problems. Where oxidation is happening? At anodes. All right, oxidation happens at anode, and anode is negative. Reduction is happening at cathode, and cathode is positive. All right. Another thing, I think that should be in chapter, this point should be in previous chapter. Whenever you are asked to write thermal equation, and anywhere in the question part A, part B, it says that this reaction is happening at SLC and it is a combustion reaction, the water is written as liquid form. All right. So because in the combustion equation, water could be gas or liquid, but most commonly, if it is happening at standard lab condition, which is normally the case, water should be in liquid state. All right. Now, now this is the atypical cell, for example, and in this cell, you are given 2 containers. You need to know everything. When they ask you to label these, make sure all the labels are outside the cell. No words are inside these beakers. All right. So again, first of all, I want you to find out the 2 half reaction which are happening, and find out the half reactions in the electrochemical series. The 1 half reaction which is on the top is happening at cathode. All right, and is gaining electrons. And the half reaction which is happening, which is at the bottom on the electrochemical series, is anode. All right. For example, in this side, there is a chlorine gas. All right, and on this side you have copper plus. So if you look for these 2 things in the electrochemical series, you'll find that chlorine is way on top in the electrochemical series, maybe 3rd or 4th from the top. So because chlorine is on the top, it is cathode. Like this side is cathode. So, all right. So wherever the cathode, remember red cat is positive. So wherever is the cathode, reduction is happening there, and that side is positive. And anox is negative. So wherever the bottom one is anode. So anode is where oxidation happens, is negative. All right. Electrons always flow to the more positive or positive side. Yeah. So electrons are flowing to the positive. You need to show all these directions. Now, whichever side is positive from the salt bridge, let's say in the salt bridge you have KCl. Whichever side is positive from the salt bridge drops on the same side. Whichever side is the negative in galvanic cell, the negative from the salt bridge drops in there. All right, these are a few common things. Now, let's say there are 2 half equations. oxidation half, reduction half. You want to add this, you cannot add two half equation until their electrons are equal. In this case, they are same number of electrons, so just add them and they'll cancel each other. But let's say if you had something else, for example, Fe2 becoming 3 or 3 becoming 1, only one electron is involved, then you need to time that half equation by 2 and then add those two equations. So you cannot basically add two half equation if the number of electrons are not the same. Another very important thing is that in your electrochemical series, I'll show you one electrochemical series. Yeah. In your electrochemical series, you see the half reactions are shown with double arrow. It's very important that if you're asked in the exam to write half equation for something and you have to copy that half equation from electrochemical series, and normally you do that, many equations are already there, you just need to copy. Do not copy this arrow as double arrow. Please remember that. You don't get full marks with that. So let's say if you have to copy chlorine, write exactly everything same. So Cl2 plus 2 electrons, but instead of double arrow, you need to write single arrow. And then write 2Cl and states everything. So double arrow is only in the electrochemical series. You do not copy double arrow in your in the questions when you answer that. Alright, like I said that in the electrochemical series, reaction is happening between two halves. So the half which is on top is this one, that will be your cathode side. And the bottom reaction is anode. So reaction always happen when you start your arrow from the oxidant, oxidizing agent, and arrow goes down like this. Alright. In galvanic cell, the reaction will not happen if your arrow goes straight or goes up. No, they will not do reaction. Your arrow must be going down from left side to the right side in an electrochemical series and going downward. Yeah. Now this becomes this. You copy that from the electrochemical series with a single arrow. Just copy that. So whatever is happening as in the cathode side, you just copy that from your electrochemical series. Do not change anything except the arrows. And whatever is undergoing oxidation, you need to reverse that equation. For example, if you see copper is 2 plus 2 electrons and become copper solid. All right. Zinc is I'm writing these two equations exactly as they are in the electrochemical series. 2 electrons becomes Zn. All right. But because the copper is higher in the electrochemical series, will not change this. When they ask us to write the reduction half equation, you just keep as it is. But don't copy zinc, because then both copper is accepting electron from where that electron is coming, from zinc. So you need to reverse that equation. All right. So you write zinc like this, and it is becoming zinc 2 plus 2 electrons. So in summary, whatever the two half reactions are there in your electrochemical series, keep the top exactly same, copy it, and make double arrow, single arrow. And the bottom one, reverse it. This side become reactant and that side become product. All right. So you reverse that. Let's see this example. By the way, you'll see this is in the start. I said that if you have reading time 15 minutes and you see this scary complicated diagrams like this, during the writing time you'll be very much under time pressure. Then you might not have enough time to spend on this. So use your reading time for this type of diagrams. All right. Secondly, if you're given this type of diagrams and you say, oh, I never saw in my textbook, I never saw in the past exam this type of diagram, don't worry. All right. Sometimes you're given big diagram, but not everything is needed when you solve that question. Look at this one, read question, come back, look again, go back, look again. It will make sense eventually. All right. For example, in this case, it says that they've given you two half equation. It is very common practice that in the exam they give you the half equations, reduction half equations with electrode potential, just as they're given to you in the electrochemical series. And when they do that, normally when those half reactions are not present in your electrochemical series, or maybe present, but they give you still have to use the same logic. This one is higher in value and this one is lower in value. If they were present in the electrochemical series, this will be on top and that will be bottom. All right. Why? Your electrochemical series is designed in a way that more positives are on top than negatives at the bottom. So it means that if these two reactions were part of your electrochemical series, this was on the top, this was bottom and this would be top. All right, because the value is more positive. Which means that if you have decided that these two chemical reactions are there in the electrochemical series, this is on top, this is on top, then this is your cathode and this is going to be your anode reaction. All right. So you don't even look at this and you already decide something. All right. Now it says that write the equation for overall discharge reaction. Discharge means the way, by the way, galvanic cell provides the energy or electricity. Like for example, if you have battery in your cell right now and it's not charging on charging port, so right now that the battery in your mobile phone is giving energy to your mobile phone for different functions. So your battery is discharging. All right. So discharging means just being used. Battery is producing electricity, which means that if you put that on charging, then it becomes electrolytic. It is reversed. So discharging means electricity is produced and it is working as a galvanic cell. And recharging means it is now becoming electrolytic cell. So there are two types of battery, primary and secondary. Remember that primary batteries only discharge. Yeah, you cannot recharge them. Secondary, which means that they are always galvanic cell only. In the secondary batteries, they can discharge, can give you electricity and can be recharged. For example, car batteries. So secondary batteries work as both galvanic cell and electrolytic cell, both. Primary batteries are only galvanic cell. Anyway, write the equation for the overall discharge direction, which means when it is happening. So when electricity is produced, the electrons flow from anode to cathode, what we discussed before. All right, just like this cell, electrons flowing from where the oxidation is happening, electrons being lost, and those electrons being attracted on the other side. All right. So we have decided based on just this number that this will be putting electron. Red cat is positive. So because it is cathode, reduction is happening here. It is gaining electron. If this is gaining electron, from where the electron is coming from here. All right. So now the one which is on top in the electrochemical series, you need to write as it is. So these anions, because they don't change their oxidation states or reduction, so you don't need to copy them. So basically Ce 4 plus, all right, it becomes Ce 3 plus, all right, and by getting one electron, and yeah. And on top, you have to reverse that direction. Remember I told you whatever direction is on the top, you can keep as it is. And the bottom one will be reversed. So bottom one has zinc. So zinc now is becoming zinc 2 plus. All right, we'll reverse that. So zinc is becoming zinc 2 plus. How do we know that? Because we have two of these. and it loses 2 electrons. All right. Now we have to add these two half equations to make full, but you can't do that unless the number of electrons are same. So number of electrons are not same. Here there's 1 electron, there are 2 electrons. So we time this by 2, so they cancel out, and then you write the full equation. So even if you have this complicated picture, it doesn't matter. Just still follow the same basics and you should be fine. By the way, about your electrochemical series, you need to remember a few things. If you look at your water equations, half equations, you have 2 water half equations. One is, don't look at H2O2, the water only. Okay, you have this. Water is undergoing oxidation. This is also oxygen equation. And then you have water undergoing reduction. All right. So whenever you have to write water as a oxidizing agent, you write this equation. And whenever you have to write water as reducing agent, you need to write this equation. All right. Similarly, the next topic I'll show you in the fuel cell. In the fuel cell, you have oxygen coming from one side and say hydrogen coming from the other side, gas. Hydrogen gas coming from this side, oxygen coming from that side. Now in the middle you have membrane. Sometimes it is PEM membrane, proton exchange membrane, which is like acidic. Sometimes you have alkaline membrane, which is OH. Now this O2 equation, sometimes they ask you to write. If it is an acidic medium, you have to make sure that you write that equation. So oxygen equation, if it is with PEM or phosphoric acid fuel cell, you need to write this equation. All right, because oxygen is always gaining electron from the other side. Doesn't matter it's H2 or it's methanol or methane. So oxygen is always receiving electron. Now there are 2 equations for oxygen. One is this and the other one is where is that? This one. All right. So there are 2 equations for oxygen where oxygen is undergoing reduction. Sorry, my mistake. Not this one. This one. All right. Remember that you have to write equation for oxygen where 4 electrons are involved, not 2. So oxygen in the fuel cell always undergoes reduction because electrons coming from the fuel other side. So if the membrane is alkaline, then you use the equation where OH is there. Remember, OH is alkaline. And if the membrane is H positive, you need to use this equation. All right. I'll show you example now. For example, in the fuel cell, of course, you need to know advantages, disadvantages, difference between fuel cell, galvanic cell, all those things. I'll quickly go over the function. So normally in the fuel cell, the oxygen is always there. So oxygen comes from this side, and in hydrogen fuel cell, hydrogen H2 enters from this side. And when hydrogen comes in, it loses electrons. All right. So the electrons flow outside and come this side and pick up by oxygen. Oxygen becomes oxide. And H, which lost electron, become H positive and flows through this membrane. All right. This membrane is semi-permeable. It will not let oxide pass through this, but H positive can pass through this because it has some properties like fluorine minus attach, which can only attract H positive, but not the other way around. And remember that between these electrodes and the membrane, there is thin layer of catalyst. In fuel cell, the electrodes they have two distinct properties which are not common in other cells. Number one, they have catalyst. They have catalyst attached on the surface, all right? And what these catalysts do, they accelerate the reaction, like the loss of electron from hydrogen or gain of electron on oxygen. Whatever is happening there, these catalysts, which are mostly nickel, they speed up the reaction. And number two, there are small pores on these electrodes, so the H positive ions can pass through. All right. So this is very common characteristics in hydrogen fuel cell or any fuel cell. So in fuel cell, this half is almost common, like oxygen is coming from this side in some form. And this side can change. You can have hydrogen here, methane here, methanol here. So based on the fuel, this is from your textbook. I recommend that you go over this and try to, for the PEM, where proton exchange membrane is there, for a hydrogen fuel cell, and for phosphoric fuel cell. These three cells out of these 6 or 7, they have same equations. For example, this is PEM, yeah, PEM. So a hydrogen becomes, this is from your electrochemical series. So hydrogen loses to electron, become this H positive. And because this is so the acidic medium, we pick the oxygen where the 4 H positives are there, all right? And that equation only. So this equation, phosphoric, exactly same. And also, so I said PEM, hydrogen fuel cell, and phosphoric. So hydrogen fuel cell is not given, but it's the same thing. So these three cells will have the same equation. It's easy. All right. These two and hydrogen fuel cell have the same equation. And solid oxide fuel cell, the oxygen just become oxide, no H positive, no OH negative. It's not acidic, not basic, just oxygen become oxide, that's it. And hydrogen with that oxide become H2O. Most of the fuel cells, you will see equations are given to you, but the equations which are in your electrochemical series may not be given to you, so you need to go over these. So fuel cells names are different based on which fuels enter, and you also need to know one thing and see the difference. Some fuel cells are running at really high temperature, like 600, 1000, and some are at low temperature. So where this temperature will make the difference, you need to know, is this positive point or negative point? Depends what the question is asking you. All right, this is very important. For alkaline cell, oxygen is used where the OH is there. You need to make sure that for alkaline cell, there are two equations in your electrochemical series. So you pick the one where the OH is present. For acidic environment, you pick the oxygen equation where OH, H positive is there. All right, rate of reaction. This is now Unit 3, area of study 2. Okay, in Unit 3, area of study 2, there are 3 chapters in your textbook: rate of reaction, and then extent of reaction, which is the Le Chatelier principle and Casey, and then third chapter is electrolysis. So Unit 3, area of study 2 is rate of reaction. Again, I'm going over some important concepts. Remember one thing, very common mistakes I found in SACs and trial exams. The amount and concentrations are two different things. In many multiple choice question, you'll see that a question after giving you some equations, some conditions, they ask you the amount of product increase, or they ask you the concentration of product increase. Remember that these two are different things. Amount will only increase if some amount is added. Like if you have chlorine gas, all right, it is 1 mole, and you don't add any mole, and the question asking the amount of chlorine increase. How can it increase if amount is not added? New chlorine is not added. But yes, concentration can be increased still with the same amount. Remember that concentration is equals to N over V. Even if you keep amount the same, number of moles not change, but you halve the volume or double the volume, concentration will change. So 1 mole in 1 liter is this concentration, but same 1 mole in 2 liters is different concentration. So amount is same, but concentration is different. All right, so amount and moles are two different things. Make sure that when you read the MCQs, multiple choice question, make sure they're asking you amount or concentration. Amount can only be changed if the product or reactant removed or added. All right, but concentration can be changed even without removing or adding product reactant. Just by changing the volume, concentration can be changed. Very, very important point. I'll make star here. Like many easy multiple choice question, students do wrong just because they don't know how amount and concentration can be different. Now, second point is that this is, I think, changing the pressure and volume will change the concentration only. Yeah, not the amount. Like I said that. If you change the volume, for example, in this case, if you increase volume, concentration will decrease. Yeah, if you 1 liter to 2 liter, if you increase the volume, concentration decreasing. If you decrease the volume, concentration will increase. So, and volume can be decreased or increased by increasing pressure or or decreasing pressure. So changing the pressure and volume will change the concentration only, not the amount. While adding or removing the reactant or product from a mixture will change both. Adding and removing one substance normally give rise to an instantaneous peak only for one peak. All right, I'll give you the example at the bottom. You need to be able to recognize the shapes of the peaks and also that is it instantaneous or slow. All right, instantaneous mean on the vertical line it goes up really quick, only on the vertical line, not going horizontally at all. All right, for example, at time 1, so there was already equilibrium between nitrogen, hydrogen and ammonia gases, all their equilibrium. And then instantaneous increases only in nitrogen. Why? Because that increase is not on 2 axes, it is only 1 axis, and that is called instantaneous. Now they from this point are not instantaneous, they are slowly decreasing or increasing. So it says here if you add or remove one substance, then it will give rise to instantaneous peak only for that one peak, and other two will respond to that change slowly. All right, so you should be able to, there are 3 times. Yeah, let's see what's happening. So the reaction is like this: N2 plus 3H2, and it gives to I think 2NH3. Yeah, is balanced, all gases. So at time 1, N2 was added. Yeah, because N2 was added, so on that time on the vertical line you see that there was change, and because that was increased to decrease its concentration, it will go on that side and will make more of NH3, which means NH3 will increase. So that's why NH3 is increasing but slowly. All right, and to make NH3 it has to use H2 with it. All right, so that's why it's going down. H2 is being used. Now again after some time there is an equilibrium. All right. And at time 2, you see all three things, NH3, H2, and N2, all three things increased. Normally, this is very common that if all three things increased, it is decrease in volume. All right. Because all they are in gases, let's say all they are in 1 liter, and all of a sudden you change it to 0.5 liters. So whatever are their number of moles present, in half liter, their concentration will be more. And that is against concentration. So if concentration of everything increase instantaneously, remember that this is also instantaneous. All right. So if concentration of everything instantaneously increase, that is decrease in volume, which means that increase in pressure. And it could be going to the possibly other direction. If instantaneous decrease is happening in all the reactant product, the volume was increased or pressure was decreased. All right. So this is the second chain. Now, if the volume was decreased and pressure was increased, so the reaction should be going that side. Why? Because there are more number of particles here, 3 plus 1, 4. And 2 here, it always go from that to that side, which means that NH3 should be increasing. And you see NH3 is increasing and N2 and 3H2 are decreasing. All right. Sorry. Yeah. H2 are decreasing. And then again, there is equilibrium. At time 3, now you see that nothing is instantaneous, so we are not adding or removing a reactant or product, because if we add or remove any of the product, concentration of that thing only should increase instantaneously or decrease instantaneously. So that's not happening. So from this point, we're not removing anything, we're not adding anything. Are we increasing volume, like or changing the pressure? No. If we increase or decrease pressure, the volume will change and will increase or decrease the concentration of all instantaneously. The only thing is we're left with is temperature. So temperature is increasing or decreasing. So this is how you look at these graphs. And remember that there are two types of graphs. One is concentration with time and other is rate with time. So in the one we're discussing now is concentration. Don't mix it with rate. We'll see ahead now. So whatever we discuss on the above is this. If you change pressure, you will see both the reactant and products increase or decrease instantaneously, not one thing. Yeah. If we change concentration, whatever the concentration is changed, that will be like increased, that will be changed, and second concentration will respond to that. And if we change temperature, there is no instantaneous peak. The things are happening slowly depending on exothermic or endothermic reaction. All right. Let's look at this question. It is endothermic reaction, and hydrogen gas and iodine gas are reacting to produce hydrogen iodide. Which one of the following statement is correct? A catalyst was added at time 2. The amount remember that catalyst is increasing rate of reaction. It's not changing amount of reaction. The amount of HI is greater at time 3 compared with the time T1. The amount of the, if amount was added, wait a second, I'll drink water. So yeah, at time 2 there is instantaneous increase in all. All right. So B can also be eliminated because we did not add any amount. Then it says the rate of reaction producing, the graph is about concentration, but the question is this C option is about rate of reaction producing HI is the same at time T1 and T3. We keep this and go to D, the rate of the production of HI, the rate of the reaction producing HI, the rate of the production of HI at time 3 is double the rate of production of H2 at time 3. Now if you look at C, it says that the rate of reaction of HI is the same as time 1 and time 3. Because the concentrations are different, rate of reaction is also different now. It's same. It's same for forward and backward reaction, but it's not same for the same product. Now rate of production of HI at time T3 is double the rate of production of H2 at time 3. If you look at the equations, HI is 1 mole and H2 is half a mole. Because their concentrations are different, so the production, when you produce HI, you produce 1 mole, but when HI produce half, H2 you produce half a mole. So production of HI is always double than the production of H2. It doesn't matter which rate. So that's quite weirdly worded, but yeah, that sounds right now. So it doesn't matter which concentration or what, according to this equation, when you do the forward reaction, whatever amount of HI is produced, when HI produces H2, that is half. So this is always double, this is backward is half. So this seems right. This is another question, I think from 2019. And here I want to mention this very important thing, that when you look at the question, you see chlorine is 4 moles, cobalt is 2 moles, cobalt chlorate is 1 mole. So 1, 1, 4, which means that this was the question and this was the solution from the same year. So this question was given to you, few drops of silver nitrate solutions are added to the equilibrium. We know that from our year 11 chemistry that AgNO3, when it reacts with chloride ion, doesn't matter sodium chloride or which chloride, but Ag then react with this and form AgCl. AgCl is precipitate, but important thing is that Ag positive loves to react with chloride. So if you have this equilibrium and you add AgNO3, basically you are removing the 4Cl. Like the chloride ions are, concentration of chloride ions are decreasing, or you can say that you're removing the product. Now if you're removing the product, then we have to make more product, so it means that this will break down. So concentration of COCl4 decreases, concentration of Cl4 is also decreasing. Why? Because Ag is like eating it. Alright, and cobalt will increase because to make more chlorine, this breaks down. When it breaks down, it also forms this. Alright, so it looks like this. COCl4 is breaking down, so concentration is decreasing. Important thing is this, you have only one box, because the ratio of COCl4 and cobalt positive is 1 to 1, so increase is also just one line. But chlorine is 4. Before the final equilibrium, you see, if it has gone only one line down, it has gone 4 lines down, and you need to maintain that ratio in your exam as well. So, and this is just one, has gone one line up in the final. Now, you might ask that how far we have to go down. Could we have come here and then gone up? But say if you come down here and go up like that, the concentration has not gone down in your final. So you have to have this 4 lines difference, which means you have to go well below that and then come back to that equilibrium. All right. So the concentration is decreased, then during the equilibrium process it comes up, and before the final concentration, sorry, the final equilibrium, still you should have this ratio of 1 to 4 to 1. All right, so this is important. These boxes are given for a reason. All right, so you have to go down, and here you have to go up just by 1, and here you have to go down just by 1. So you need to have this ratio maintained. Very important. Now Kc value, we know that Kc is basically concentration of product over concentration of reactant in simple terms, and whatever coefficient are given, they become power. Yeah, Kc does not have a fixed unit. It depends after cancelling what is left over. For example, in this case, each concentration is capital M. So there are 2 M's there on top, M time M, and there are 3 M's at the bottom. All right, so 2 will cancel by 2, the 1 left. So in this case, the Kc unit would be M minus 1. So Kc could have different units, maybe no unit at all, if all the concentrations are cancelled. Now, important thing to remember is that in Kc, when you have the concentration of product 1, product 2, and reactant 1 and reactant 2, you only have this concentration from equilibrium. If you put some concentration which is before equilibrium, after equilibrium, you'll get wrong answer. So in the question you might be given some initial concentration. You cannot put initial concentration in Kc expression. You need to have concentration when the equilibrium has reached. Number 1. Number 2, it says concentration. So if something is pure liquid or pure solid, for example carbon, or for example water, you cannot put them in the Kc expression. Why? Because it says concentration. Concentration is always solute in the solvent. If something is just one, pure water, concentration of what? So you cannot use pure water or pure solid, because they are not expressed as concentration. All right, remember 2 things. 1, you only use concentration when the equilibrium has reached for this Kc thing. And second, pure liquid and pure solid can't be part of the Kc. If you're not given all the concentrations at equilibrium, then you have to use the Rice method or ICE method. Rice method means first you write a balanced reaction, then write the initial moles, change in the moles, final moles, and whatever volume is given, divide by that to find the concentration. All right. So in this case, for example, 1 mole of SO2 and 1 mole of oxygen are placed into an evacuated sealed 3-liter container. They have just placed in there. The final reaction has not even started. So let alone the question of reaching at equilibrium. So these 2 are initial concentration. After the reaction reaches equilibrium, the container contains 20 grams of sulfur dioxide. You can easily find moles of this, right? Like you have moles of this here. You can find moles of this by 20 gram divided by whatever is the molar mass of sulfur trioxide. So 32 plus 16 plus 16 plus 16. You'll have moles of this. This is the only moles given to you which are at equilibrium. All right. So what you have to do, you write a balanced chemical equation. You've done that. write the initial moles. So initial mean whatever given to you initially. So you have 1 mole of SO2, 1 mole of oxygen, and nothing is given at equilibrium. Nothing is formed basically initially. Now change mean that when basically when the reaction proceeds, 2 moles of SO2 will be used up, so minus 2x. 1 mole of oxygen will be used up, and together they will produce mean add 2 moles of SO3. So this is the change happening. All right, so this is you have written here. Plus 2x mean when the reaction starts, this change will happen. Every 2 moles will be minused from SO2, because you read it like this: 2 moles of SO2 react with 1 mole of oxygen, produce 2 moles of SO3. So 2 moles of sulfur dioxide is used up, and it uses 1 mole of the oxygen, and it gives you 2 moles of this. Now what it means in the given scenario, it says that after you have found the moles from here, it says that 0.25 moles of SO2 are formed. So we know that if 0.25 moles of SO2 are present, they are 2x, not x. So whatever moles of SO2 are there, they are 2x. If they're 2x, 1x will be half of that. So 0.2 half of that is 0.125. Yeah. So you have 0.125 moles is the x, but initially you have this much present, so you have to minus this from this. So 1 is the initial 1 present initially, you minus it, this amount, and you have this much left over. All right, and because 1x is 0.125, 2x is 0.25, so 0.25 is also minus from here. You have, so now at this stage you have all the moles at equilibrium. Now remember that in Kc you don't put moles, you have to have concentrations. Yeah, so you have moles now divided by the volume given to you, which is 3 liter. All the moles divided by 3, and you'll have concentrations. Yeah, concentration of food. At this stage now all the units are in all the values are in concentration. You can put in there, and even you can go wrong here if the Kc expression is wrong. All right, because Kc is equals to product and the coefficient become the unit, so you have to write SO3 and 2. Why? Because in the balance equation you have coefficient 2. So if you don't write this 2 here, for example, even concentration is right, you will lose marks from this point. And here I'm saying that this type of question is 3 to 4 marks. So you'll get maybe 1 mark for doing this, and 2nd mark for writing maybe correct Kc expression, and 3rd mark for your final answer. So make sure you show all these steps. Each step is, you may lose maybe only 1 mark from here if you do something wrong, but at least you'll have these 2 marks. So if you do everything in calculator, and you just, even if they were right and your answer is wrong, you lose all 3 marks. So make sure you show the working out. All right, so from Kc expression, basically you need to know is that how to write correct Kc expression. And Kc is different from quotient, which is Kc is concentration at equilibrium and Q is concentration at any other point. All right, and the calculation of Kc in different method. If all the values are given at equilibrium, just put them in and find Kc and write the unit. If some are given initial, some are given final, then use Rice method. Now, before I showed you this graph, this was concentration versus time. So you'll see that concentration of some things decrease, something increase. It's very common, but in rate graph is different. Let's see, very important. And student normally misunderstand or for some reason don't understand this concept well. When you're given a question which has, for example, A plus B, and it's a reversible reaction, C plus D, and let's say it is exothermic, all right? Exothermic means that if you decrease pressure, it will favor the forward reaction. If you increase pressure, it will favor the backward reaction. But students mix this equilibrium shift with rate of reaction. Please don't do that. Why? When you increase temperature, the kinetic energy of all the molecule increase. They move more frequently than before, and the more effective collision and rate of both increases. Remember that the chemical shift could be one side, all right, or one of the forward or backward reaction is favored, but rate of reaction, no. Rate of reaction of both will increase if you increase temperature, of both will decrease if you decrease temperature. Doesn't matter it's exothermic or endothermic. After that something else happens, you need to know that. But rate of reaction is always increasing the reaction, all right, and increase in temperature is always increasing the rate of reaction, and decrease in temperature is always decreasing the rate of reaction. Let's see more detail maybe. So remember the following points. Increase in temperature increases the average kinetic energy, leading to increase in frequency. By the way, this is very important, very, very important, all right? If you write in the collision theory, if you write that or increase in temperature increases the number of collision, you will not get marks for that. It increases frequency of collision or increases the number of collision per second. You need to say this per second, or instead of saying whole this thing, you just say frequency of collision or collision frequency. Just saying that increase in temperature will increase the number of collision will not give you marks. This is technical thing. Please remember that. So increase in temperature increases the average kinetic energy of molecules, leading to increased frequency of collision or increased number of collision per second, which increases the effective collision. All right. Increase in temperature leads to an increased proportion or percentage of the total collision that are successful. You must either say frequency of collision or say number of collision per second to get full marks. If you only say, which I don't want you to say, temperature increases collision, you may not get full marks. If there's 2 mark question, you'll get maybe 1 or not the 1 even. Okay, and second important thing, I want you to know this really well. If the question is talking about the rate, it's not saying shift, chemical shift, or which reaction is favored. This language is not there, all right? If it says rate only, please talk about collision theory, the one we discussed about. Increase in temperature will increase the rate of the average kinetic energy, which will increase the frequency of collision, and talk about that. But if the question is talking about which side reaction will be favored, or which product will be produced more, or which side the reaction will shift, there's no rate thing in there, then talk about Le Chatelier principle, all right? So when it comes to temperature, students are confused. Sometimes you use collision theory, sometimes you use Le Chatelier principle. Use collision theory only when they are talking about the rate of reaction, and use the Le Chatelier principle if they are talking about the percent yield or which side the reaction will shift. Yeah. And in the rate or reaction, normally the reaction is given, you'll see single arrow most commonly. All right, let's see this question now. Ammonia is produced from this reaction and it is exothermic. You can see that minus charge. Ammonia can be produced by reaction of hydrogen and nitrogen. When this reaction takes place in a sealed container, equilibrium. Okay. If the pressure and the volume remains constant, when the temperature is increased, the forward reaction rate will, alright, important thing, rate will increase. Now there are two things. They said rate here and they said concentration here. Remember that this means concentration of ammonia. So many students easily miss one of the two things. Easily they say, oh, rate will increase and pick it and go. There are two things. There is one rate here and then there is concentration as well. Now you decide that it is exothermic reaction. Forget rate for a minute. It is exothermic reaction. Exothermic reaction, forward reaction is exothermic reaction, all right, and backward is endo, of course. So increase in temperature favors backward reaction always, yeah. So which means that if the temperature is increased, the backward reaction is favored, which means that ammonia will decrease. The concentration of ammonia will decrease. Now concentration of ammonia will decrease is here mentioned here and here. Now remember that I told you previously that when the temperature is increased, the rate of reaction increased always, doesn't matter exo or endo. All right, so I'm sure it's this one, because it says that temperature, or you can pick this question in another way. It says temperature is increased, the forward reaction rate will, increase because the rate will increase anyway. So temperature increase will always increase the rate. So when it says that temperature is increased, the forward reaction rate will increase. So both are increased, yeah, increase. This increases for rate. But then there's another thing. The concentration of NH3 will increase or decrease. Because the backward is endothermic, the backward reaction is favored, which means that more nitrogen and hydrogen will form and ammonia will decrease. So this becomes wrong then. All right, these are very tricky questions. The graph below shows the rate of the forward reaction and reverse reaction. Now remember that this graph is not against concentration. This is rate of reaction. All right. So this equation gives you endothermic reaction. Delta H is more than 0, which is positive something. Endothermic reaction, yeah, is it? Yeah. The graph shows that the rate of forward reaction and reverse reaction versus time. A single change is made to equilibrium mixture at time t1 and equilibrium is re-established at time 2. And we see that reverse reaction is increased. The rate of both reactions increased, yeah. Rate of both reaction, forward and backward, increased. But rate of forward reaction increased to the less extent and rate of backward reaction increased more. Okay. First one we can eliminate right away because the noble gases don't disturb equilibrium. Then you have B, C, and D. At time 1, reactants are removed. Remember, if the reactant concentration, if the reactant are removed, the number of particles decrease. Yeah, reactants are removed, the number of particles decreased, and number of particles means the frequency of collision also decreased, so number of collision per second also decreased, and the forward reaction should decrease. Here the forward reaction is increasing. It doesn't matter slow, but it's increasing. So if the reactant or products are removed, there is a decrease in concentration, which leads to decrease in collision frequency, which leads to slowing down the reaction of that side. Rate of reaction slows down if you remove the reactant or product. The amount of product is higher at time 2 compared to just before time 1. The amount of product is higher. Wait a second, and then the change made at T1 results in increase in equilibrium constant at time 2. Alright, so answer is COD. Let's see the question. It is endothermic. Endothermic mean the reaction is increase in temperature will favor A and B, and rate of should be higher. The amount of product is higher at time 2 compared to now these two questions, the equilibrium constant, which is Kc, can only be changed if the temperature is increased. If anything else is changed, it cannot change the value of Kc. But if the temperature is changed, it will change the Kc. The thing is that amount of product is higher. That is possible. If the product is added here, you'll see the rate of backward reaction, reverse reaction going, you'll see a instantaneous increase in the rate of reverse reaction. Because why? Because you added the product. Now product after adding will slow down or will decrease because it's trying to make the reactant. But still, after the equilibrium is reached, the product of the concentration of product is still higher. Does that make sense? We added C and D, and that caused reverse reaction to be really fast, so it goes up. Now to decrease the concentration, it moves in this direction, so C and D comes down and A and B go up. But once the equilibrium is reached, that C and D is still higher than the very initial one. Alright, so that makes more, the amount of product is higher at time 2 compared to just before time. Yeah. So sometimes you have to focus, is asking about rate of reaction or concentration of reaction, amount of reaction. Now complete the following. I'm not sure it was the exothermic or endothermic, but I'll just tell you. Complete the following rate time graph to show the effect of decreasing in temperature. Now important thing is that it is rate and this is decrease in temperature. So whenever temperature is increased, rate of reaction will increase, doesn't matter what. And this question could have been asked in different way. One, let's say the temperature was changed in this reaction, and then they give you this graph, they ask you. So you say that because the rate is going down and there is a change in temperature, only decrease in temperature can decrease the rate, increase in temperature will increase the rate. So if there's certain reaction, you'll see that the temperature of the rate of both reaction, forward and backward, will decrease, but one will decrease more than the other. Now it depends, it's exothermic or endothermic. Now the exothermic reactions, they favor decrease in reaction. So this particular graph is for exothermic reaction. So this is forward reaction and this is reverse reaction. So both are decreasing their rate, but the one which is exothermic and you're decreasing temperature, its rate goes down more than the forward reaction, the backward reaction, which is endothermic and needs temperature. So if you decrease in temperature, graphs looks like this. If you increase in temperature, and it should look like this. One will go like that, and another will go like that. So increase in temperature will increase, and decrease in temperature will decrease. Then Maxwell-Boltzmann curve, where every year without exception, this is again in chapter 8, I guess, very common question. Every year you'll see one graph like this. So basically what's happening here, at any time during a reaction, you have number of particles here, and you see their kinetic energy. All right, so kinetic energy is increasing from, let's say, 0 to 1, 2, 3 up to there, and effect of decrease in temperature. So if this is happening at certain temperature, let's say 40 degree, and you decrease temperature to 25, they ask you to redraw the graph. What will happen? So remember that if temperature is decreased, so if you have this and temperature is decreased, the graph you want to show is like that. You need to increase the intensity and decrease the width on the energy. Yeah, so this is at lower temperature. So this was at higher temperature. If they ask you what the graph will look like at lower temperature, so just increase the intensity and pretty much go there. All right, and it shifts, the shoulder is shifting to the left. You can't go just increase intensity and go there back. No, you have to shift the shoulder. If it was here, now it's here. All right, and reverse is true for let's say this was the lower temperature. All right, let's say 25, and then the increased temperature, so you need to decrease the size of peak and shift to the right. All right, so size is going down from the peak size from here to here, and from here to here is now move to the left. So Boltzmann, this curve is very important. They ask you two questions: one about activation energy, and other about how it will look like if temperature is decreased or increased. So remember that if temperature is decreased, you increase the intensity, number of particles going up, but at the same time the shoulder shift to the left. And if temperature is going from higher to lower, from lower to higher, so you decrease the size of the peak and shift to the right. All right, and what catalyst does? Catalyst change the pathway of the reaction, and let's say activation energy was here, I don't know, let's say 10. The catalyst and all these particles which have minimum this much energy, only this many, are doing the reaction. All right, now what catalyst does, it decreases the activation energy for that reaction, and now more activation energy is now with catalyst and without catalyst. Now more number of particles are eligible for this reaction, you can say that. All right, so the second thing is this: how they might give you a graph like this. Say that this is the activation energy, now you have catalyst, how the reaction will look like. So just maybe kind of here and say that now this many particles have activation energy. Why? Because the catalyst, they lower the activation energy of the particles. All right, so this is very important as well. Electrolytic cell, chapter 9, all right, of your textbook. And with this, unit 3 is completed. Electrolytic cells are different from galvanic cell. Electrolytic cell, now normally when you see in the exam, if there are two separate container or somehow the two containers are separated, the galvanic cell. Electrolytic cell is within one container mostly, and you'll see the electricity is provided first and then that causes reaction. While here in the galvanic cell, the reaction occurs first and that gives you electricity. So here's some differences. Galvanic cell, they produce electricity. Electrolytic cell, they consume electricity, and they are spontaneous reaction. Spontaneous mean you just leave them together under right condition, they will react. They don't need energy. Non-spontaneous mean you put them together, they will not react. You need a push, which is electricity, to start them to react. In this case, galvanic cell chemical energy becomes electricity or electrical energy. In that case, you need to provide electricity, and that gives you chemical reaction or chemical energy. Very important here, anode is negative, cathode is positive. Like I said, red cat is positive. That's true for galvanic cell. Anode is positive. Still oxidation is happening here. That is true in both cases. Oxidation is still happening at anode and reduction is happening at cathode. But oxidation is happening at anode, oxidation is happening at anode. That's true for both, for all cells. But in galvanic cell, anode with oxidation is happening is negative, and here anode with oxidation is happening is positive. Now electroplating is what? You have a metal, maybe it is very reactive metal, and you want to protect it, and you want to have a thin coating of another metal. It could be to beautify that or to make it unreactive, the top layer. That is called electroplating. So electroplating is how? So you have this, let's say, negatively charged electrode, and the one you want to plate on top of that is, let's say, metal X, 2 positive. Now these cations travel to this, accept the electrons there and deposit there. All right. So now for this electroplating to happen, you need to have that plate which you want to electroplate must be negative, which means that in the electrolytic cell it should be anode. Yeah, sorry, red cat is negative in this case. Yeah, cathode. So the metal where you want to plate want to deposit the thin layer of other metals electroplating, that must be cathode. If you attach a metal with anode and you think that it can be plated, no, it cannot be, because it's negatively charged. Sorry, it's positively charged. Anode is positively charged, and metal cannot travel that side. All right. So look at this. In this case, for example, the copper here is, let's say, whatever metal is here, that metal is negatively charged, and copper from the solution are traveling towards that and depositing there. So this thin layer is deposited there, and the copper anode is also dissolving and becoming this. So in electroplating, the metal which are being plated become larger in size, and the metal which is being dissolved becoming smaller in size. All right, this is electroplating. The important thing you need to know is that the metal which you want to electroplate cannot be anode, must be cathode. So electroplating is a process that uses electrolysis to deposit a layer of metal ion on the surface of another material. The object to be plated is connected by a wire to the negative terminal, making it cathode. So the metal which you want to, for example, if you have a spoon, you need to attach to the negative, so it becomes negatively charged and attract positive from the solution. Size of the anode decreases. Why? Because it's dissolving and depositing on the other side. And size of the cathode increases. Why? It is being plated. Now, some reactions. I told you in the galvanic cell that oxidizing agent is here, reducing agent is here, your arrow must go down. Don't look at this in the electrolytic cell. in the electrolytic cell there is a competition. So the two things which are undergoing oxidation, are oxidizing agent, look for those on the electrochemical series, and the one which is on top will undergo oxidation, and then look for the two reducing agent and look for those in the electrochemical series. The one at the bottom will undergo reduction. Doesn't matter arrow goes up or down, but normally in electrolysis, because non-spontaneous, arrow goes up. So don't worry about the arrow, I'm saying that. Just for example, look at this one. This is a container with 1 molar potassium iodide solution. It is solution, which means that water is also there. All right. So you have this container. It has potassium iodide and water. If it is AQA, because when it says, even if it doesn't say that, when it says its concentration is 1 m, concentration means potassium iodide is dissolved in water. Otherwise, it would be liquid or molten state. All right. If it is concentration, it means 1 mole of potassium iodide is dissolved in 1 liter of water to make solution. So water is there. Now, if you see oxidizing agent, the left side of the electrochemical series oxidizing agent, there are two possible: potassium and water. All right. And reducing agent, which are on the right side of the electrochemical series, are iodide and still water. Water can act as both. Now, I said that list like this, the oxidizing agent and reducing agent possible if the electrodes were not inert. I would also write them in the list, but they're inert, so we don't write. And then now oxidizing agent, the rule says this: in the electrolysis, all the oxidizing agents you listed, the one on the top in the electrochemical series will react. Now, if you look at in your period in the electrochemical series, the potassium is right at the bottom, very close to lithium, sodium. Potassium is there, but water is on top. So from the oxidizing agent, water will react. All right. And remember, water has two equation. You have to pick the equation which is water is oxidizing agent. All right. So water becomes this. All right. And on the reducing agent side, there are iodine and water. So iodide is at the bottom in the list and water is on top. And when you see oxidizing agent, so iodide will react. So in electrolysis, you need to see that what are the possible oxidizing agent, list them. The one on the top will react, and then make the list of reducing agent. Now, if you make this arrow, it will be in the electrochemicals, it will be going like that. That's okay, because this is non-spontaneous reaction. Faraday's two laws, and based on that, you have basically, if you know these two formulas or three formulas, Q is equals to IT, Q is equals to NE. I think you have these in your data book, at least the second one as well. So by rearranging this formula, you can also make number of moles of electron. E mean number of moles of electrons are charge. Q is charge over Faraday, which is 96,500 coulombs. So F is a constant which is equal to 96,500. Q is charge, which you can find by multiplying I, which is current, with time. Important thing is that time must be in seconds. All right. This is basically based on the second law of Faraday's. Faraday says that don't worry about the law. What it's now, once you have found the moles, 1 mole of electrons will deposit or produce 1 mole of Ag. Because in the calculation, you have to find out the mass or moles of metals deposited, yeah, on the electroplating. So why 1 mole of electron? Because the equation is Ag plus 1 electron and become 1 mole of electron become Ag. So for each 1 mole of Ag, you just need 1 mole of electron. So if using this formula you find moles of electron, Ag is also same. So you can say that only in case of Ag, number of moles of electrons are equal to number of moles of Ag. Alright, or anything which is 1 mole. Similarly, it says that 2 moles of electrons will deposit 1 mole of copper. Why? Because copper equation is this: copper plus 2 electrons become copper solid. So for each 1 mole you want to deposit, you need 2 moles of electrons. So if using this formula, you find that Ne is a number of moles of electrons of copper or whatever, the number of moles of electrons for copper you found out, number of moles of copper would be half of that. Why? For each 2 moles you deposit 1 mole. So yeah, so whatever number of moles for electrons you find out for copper, the copper will be half of that. So once you know the moles of metal like Ag or copper, simply use those moles, multiply with the molar mass of copper or Ag, and you will find mass. Alright, and molar mass you can find from the periodic table. Let's say this example: how many grams of gold? To find the grams of gold, first you need moles of gold, Au. And to find the moles of gold, you need moles of electrons. And to find moles of electrons, so work backward. To find moles of electrons, you need moles of electrons, Q over F, let's say. Oh, and to find Q, you have Q is equals to I times T. So you can backward work like this. How many grams of gold will be deposited when the 500 coulomb, this is Q, pass through a solution by the following equation? Okay, they've given you already charge, so you don't need to find this. So use this to find number of moles of electrons. So number of moles of electrons are this, yeah. Now according to the equation, to produce 1 mole of Au, you need 3 moles of electrons, which means that whatever moles you found for electrons divided by 3 will give you the moles of Au. Alright, so this is what you do: divide by 3 and you get this many moles of Au. Once you have moles, time it by the molar mass, which is this, and you'll have mass of gold deposited in gram. So here we completed unit 3, and I'll start unit 4 in the second recording. Please, just before you go, that night, go over these concepts again. Just go listen to this recording. It's very important for you guys, because these are the common mistakes I found in you guys. So pay attention. I'll start unit 4 now in the second recording. All right, thank you. Assalamu alaikum.